Hello, this is Barry Evans with Penn State University. In this next and final subunit, we will be completing the analyses that we've started in previous exercises as part of the case study series. Specifically, we will be using the GWLFE model to simulate various load reductions that might be achieved via the implementation of a variety of best management practices, or BMPs, within the Big Hollow watershed in central Pennsylvania. Before we begin our modeling, however, let's review some of the material that was presented in previous exercises to see where we are and what we need to do. This next slide is one that we had seen in the first subunit of this case study series. This slide basically lays out the steps that we were going to take for the purpose of our case study. We were first going to use MapShed to create an input file for the GWLF model for the watershed of interest, in our case the Big Hollow watershed. We were then going to run the GWLF model to estimate a new baseline load for the watershed. In this case, this is the load without any proposed BMPs that might be implemented in the future. And the next two associated steps, or related steps, we would then develop BMP scenarios in the GWLFE model using the Bmp Editor tool and run these scenarios iteratively until a target load reduction has been achieved. So, up to this point, we have already completed the first two steps. This means we are now ready to run various BMP scenarios within the GWLFE model. Before we do this, however, let's take a look at the target load reductions that need to be achieved in this particular area. This next slide, which was also shown previously, summarized the results from a previous TMDL that we assumed was done for the Big Hollow watershed. In this case, the streams in the Big Hollow subwatershed were determined to be sediment impaired. Therefore, the focus of the watershed improvement plan was determined to be sediment. The baseline sediment load as a result of previous modeling was estimated to be 2,721 tons per year, and the waste load allocation assigned to the Big Hollow watershed was determined to be 2,122 tons per year. Therefore, the sediment load target reduction is the difference between these two, which is equal to 599 tons per year, which translates to a 22% reduction in sediment, which is the target goal. As part of the same modeling, the baseline load for Patton Township was estimated to be 619 tons per year. Therefore, the target reduction for the township can be set at 619 times 0.22, which is equal to 136 tons per year. However, as suggested by recent guidance from the Pennsylvania DEP, the emphasis for a study of this type should be on the percent reduction rather than mass reduction, or the waste load allocation as determined by the original TMDL. In our case, we used the GWLFE model to calculate a new baseline load, and it is this baseline load that will be used as the basis for determining whether any reduction might be possible through the implementation of future BMPs in our study area. Furthermore, for analyses of this type, municipalities are only responsible for addressing pollutant loads and associated load reductions that pertain to their particular MS4 area. Therefore, since for the purposes of this case study, we are assuming that when you are working on behalf of Patton Township, we will only focus on Patton Township loads and will be applying the 22% reduction requirement to the new baseline load calculated for Patton Township. Okay, so let us now take a look at the sediment reductions that we will be required to simulate as part of our upcoming modeling. First, as a result of a previous study, that is the original TMDL, the old baseline load for Patton Township was estimated to be 619 tons per year, which translates to 1,238,000 pounds per year. The new baseline load, based on a new modeling that we completed with MapShed, is now 1,145,691 pounds per year, which translates to 572.8 tons per year, which is our new baseline. The percent sediment reduction required for the Big Hollow watershed was calculated to be 22% based on the original TMDL data, and this percent reduction also applies to Patton Township. Therefore, the sediment reduction target for Patton Township can be calculated as 0.22 times 572.8, which is equal to 126 tons per year. As part of the new MapShed modeling also, the new baseline load for the entire Big Hollow watershed was estimated to be 2,625.7 tons per year. Therefore, the goal in our new modeling will be to use GWLFE to simulate Bmp-based reductions that will reduce the watershed load from 2,625.7 tons per year, which is the new baseline load for the watershed, to 2,499.7 tons per year, which is the baseline minus the load reduction. And that's what we will try to achieve with the modeling that we will now start. Now that we've defined our target reduction goal for the watershed and for the township, let's now open up the GWLFE model and begin modeling. As you recall, we can get to the model through the MapShed interface, or we can go right to the model executable, which is located in the models folder underneath the MapShed directory. So if we go to models, we can go right to the GWLFE model. We double click on that. We click on run and open up the model. I'm going to minimize this window in the back. And we can either open up an input file, which we don't need to do at this point, or look at the average output, or use the Bmp Editor. The Bmp Data button here allows us to do different Bmp scenarios within the model. But before we do that, let's take a look at the model output again for the Big Hollow watershed to see if we can gain some insight into what the loads are, where they come from, and what we might be able to do in terms of Bmp implementation. So, if we click on average output, and let's specify English values at this point, we can then open up an output file, and we will open up the output file for the Big Hollow watershed, which is located in the output folder underneath Big Hollow. And the Big Hollow watershed, as you recall, has a number of 7283. That's the ID. We can double click on this and then view the output. So let's go to the monthly loads and then loads by source. So, as indicated earlier, the load that was the sediment load that was estimated or calculated for the Big Hollow watershed was 2,625.7 tons per year. As shown by this cell here, the bulk of these sediment loads are coming from stream bank erosion. This tells us that we need to either implement BMPs that reduce the erosion along stream banks themselves, or implement BMPs that reduce peak flows that cause the stream bank erosion initially. We also have some upland loads coming from agricultural areas such as hay and pasture and cropland, which may or may not be reducible with BMPs. And we've got loads coming from different types of residential settings, from low density, medium density, and high density, and mixed in residential areas. And we may be able to apply BMPs in these areas to control upland loads. So it looks like we are going to have to implement a mix of BMPs that reduce stream bank erosion principally, and maybe some additional BMPs that reduce upland loads from urban and maybe other areas as well. So, before we begin implementing any BMPs, let's take a look at the Bmp Data Editor. First, let's load an input file. Again, we will load the input file that we created for the Big Hollow. This is Big Hollow _7238. Again, 7238 is the ID for Big Hollow watershed. We load that. At this point, we can, of course, look at transport data and nutrient data, which we don't need to do anymore since we've already run the model. But we will, in this case, primarily be using the Bmp Data button, which is the Bmp Editor tool, if you will, to basically specify the implementation of various rural land and developed land BMPs. So when we click on that button, we're first presented with the BMP and the form for implementing rural land BMPs, which are primarily agricultural BMPs. And if we put our cursor over any of these titles at the top, we can see what types of BMPs these actually indicate. Now, we probably in this exercise will not implement any rural land BMPs, but we'll go right to the urban Bmp editor, which we can get to with this button right here. In the urban Bmp editor, we have a variety of different BMPs that can be simulated for the purpose of estimating potential load reductions. And before we start specifying any of these BMPs for our particular area, it will probably be worth spending a little bit of time to describe what each of these BMP functions are and how they work. Okay, so let's look at the detention basins option first. In GWLFE, we can simulate the implementation of detention basins. However, we don't have the ability to indicate the location of multiple basins. Rather, the way this particular tool works is that we can specify the sum total of all basins, all detention basins within our watershed area. So if we've got 10, 20 different detention basins that either exist or that we wish to implement, we have to specify what is the sum total of each of these parameters for all of the basins within that area. For example, we have to say what is the total detention basin volume, what is the total basin dead storage and basin surface area, etc. And this is treated as one large super basin to capture runoff and reduce flows and loads from these particular features. Next, we have the ability to indicate stream protection features, primarily vegetative buffer. So what we do here is we indicate the width, or the typical width, of a vegetative buffer strip along a stream and how much of that stream is actually treated. What has been calculated by MapShed is the total length of streams in non-agricultural areas. So if we indicate a fraction, by the way, 0 to 1 means 0 to 100%. So if we type in a 1, we mean that 100% of all of the streams will be treated with a vegetated buffer, and then we just need to specify what the typical width of. Typically, or usually, we don't have that much in terms of stream buffers. So we might specify, for example, maybe 0.2 would indicate 20% of the streams have buffers that are constructed along them, for example. Another option we have is infiltration bioretention BMPs, and there are a number of different BMPs that fall under this category. Usually what we do with this is to indicate the amount of runoff that is retained after a storm event. These BMPs are typically designed to capture a certain amount of the runoff from a particular storm event. Might be maybe up to half an inch or so of the runoff is captured. And here we need to specify the runoff retention in centimeters. So 1 inch is equal to 2.54 centimeters, and half an inch runoff capture might be somewhere in the order of maybe 1.25 centimeters of runoff or rainfall is captured before runoff occurs. And again, we also have to indicate what fraction of the total area is treated with this particular BMP. Again, we have the option of specifying from 0 to 1 or 0 to 100%. With constructed wetlands, we have already been given a total of urban area as determined by MapShed using land use cover data. So in Big Hollow watershed, we have 2,070 hectares of urban land. And what we can do is specify how much of this total urban land, or how much of the runoff from this particular urban land, is captured by constructed wetlands or BMPs that function similar to constructed wetlands. Street sweeping, what we do here is indicate how many times per month street sweeping occurs. Obviously it can be 0 or it can be 1, 2, 3 times per month depending on locality, but here we can indicate using a number how many times per month street sweeping occurs. With impervious surface reduction, we have to specify 2 things. Number 1, we have to say how much of the area, in this case low density mixed, medium density mixed, high density mixed, and low density residential, medium density residential, high density residential. We have to say how much of each of these areas are treated by this particular measure. So if 50% of high density mixed is treated, we would say 0.5 for 50%. We also have to say how much of the impervious surface is reduced. So if all of the impervious area within a high, let's say the impervious area within a high density is reduced by 25%, we would say we have a 25% reduction of impervious surface area across 50% of the high density mixed area. Finally, we have another, this is a new option, refers to what's called a CSN tool or the Chesapeake Stormwater Network tool. This is not fully operational yet, but what this is intended to do is to allow users of the CNT tool to indicate output from the tool here. So for example, you can indicate what type of storm event was simulated, how much of that area was simulated, and typically with the CSN tool you get a load reduced per storm event. And what the GWLFE model does is translates a single event storm reduction, a reduced load that occurs for one single event, to a mean annual load across the watershed. Again, this tool is not fully operational right now, but will be by the middle of 2015. So that's a short summary of what some of these urban BMPs are. Now let's move on to the next step, which is actually to specify some level of BMP implementation within the Big Hollow watershed. Now, before we begin our new modeling, let's go back and reset some of these values that we've edited back to 0. So that we can start fresh. Okay, and then I'll close this. Let's just take one more look at the loads that we currently have in a watershed. Again, Big Hollow 7238. So our current baseline load is 2625, 2,625.7 tons. And to help us, I have typed that into a calculator here. So that's our starting baseline load that we have to reduce. And what we need to get to, and I'll put this in another calculator, is 2,499.7 tons. This is a 22% reduction in sediment in this case. So what we're going to do is, we've already got this input file loaded. We're going to edit that using the Bmp Data Editor. And we're going to rerun the model and give it a new name. So let us call this new run, let's say with Bmps 1. So let's click on the Bmp data. Let's go right to the Urban Bmp Editor, Data Editor, and let's type in some values that represent what we currently have in our watershed, under the assumption that since the TMDL was first done, a number of Bmps have been implemented over the years. So let's assume that, for example, street sweeping is typically done in our area. And in our case, let's say it's 2 times a month starting in April. And that runs through, say, let's say November. Let's also say that some buffer strips were put in. And let's say that essentially, let's say 5% of the streams were buffered since the time the TMDL was first done. Let's also say that some stream bank stabilization occurred over that period. Stream bank stabilization basically implies that some type of bank reinforcement was done using maybe geotextiles or some other type of reinforcement. Let's say that perhaps 0.1 kilometers of streams were stabilized with some type of feature reinforcement. Let's also say that some type of infiltration Bmp was used to capture, let's say 1.5 centimeters of rainfall before runoff occurred within urban areas. And that within the urban areas, about maybe 1%. Now let's make that bigger. Let's say 5% of the area was treated with this type of infiltration bioretention Bmp. So let's stop here and say that this represents our current Bmp picture. We enter this information and then we say save in order to save these changes. Let's now run the model. And then let's look at the average output. Again, let's use the English value option. Let's browse to the output folder and see we have here, in addition to our initial model run, we now have another run with Bmps. Let's double click on that. And let's view the output. Again, let's look at the loads by source. So we now have, in terms of sediment load, a new value of 2,511.6 tons. This is lower than our initial starting point of 2,625.7, but it's still higher than our goal of 2,499.7 tons that we are trying to reach. We're not that far from it, though. So what we now need to do is add some additional Bmps. So let's close this. Let's go to our Bmp data, Urban Bmp Editor. Let's say now we were going to look at some proposed Bmps that we'll implement in the future. Let's say that we're going to, since most of our load is coming from stream bank, maybe we'll want to address stream bank erosion first. So let's say that we're going to increase the 0.1 kilometers of stabilized stream bank up to perhaps well, let's increase that to maybe 9 kilometers of stream bank stabilization. And let's also say that we're going to put some buffer strips in there, some additional buffer strips, and that will increase the initial 5% of vegetated buffer strips to, let's say we're going to increase that to 20%. Let's now save this. Let's change the output file to with Bmps 2 and run this input file again. And let's look at the new output. Again, specify English. Browse to the folder, and now we have with Bmps 2. Let's open that up and view the output. Again, monthly loads, loads by source. We are now at 2,476.8 tons per year, which means that we are now below our target load. And if we wish, we can go back and change that, our input data, to maybe have less of a reduction than we had simulated before. However, since the objective of this particular exercise is to illustrate how this tool can be used to simulate reductions given different combinations of BMPs, let's leave it at that. In our case, it's obvious that the scenario we did simulate allowed us to achieve the reduction goal that we set out for ourselves in this particular watershed. With this tool, we can also obviously achieve similar reductions with different combinations of BMPs. And if we had unit cost information, we could even look at different combinations to see what might be the most cost-effective solution in this particular area. In terms of the reductions achieved, let me clarify a point that I made a few minutes ago. That is, the difference between the starting load of 2625.7 tons and 2499.7 tons, it does represent a 22% reduction, but not in the Big Hollow watershed. The difference between these two numbers is 126 tons, as we had calculated previously, and this 126-ton reduction represents only a 22% reduction in the MS4 area that pertains to Patton Township. And the BMPs that were simulated that were assumed to either be existing or proposed BMPs were assumed to only pertain to Patton Township. In a case where there are multiple jurisdictions occurring within a given watershed where each has the responsibility of making mandated reductions as a result of a TMDL, each of the municipalities or jurisdictions would have to estimate their particular load reduction target, as we have done for Patton Township, and then use the model in a similar fashion to the way we did here in our case study. Okay, so let's briefly recap what we've done in the Unit 8 case study. I will open up a PowerPoint and let's summarize some of the activities we completed. First, as part of a previous TMDL, we assumed that the sediment reduction target for the Big Hollow watershed and all the MS4 areas within is 22%. We then used MapShed and the GWLFE model to calculate a new baseline load for the entire Big Hollow watershed, and this was estimated to be 2,625.7 tons per year. We looked at the output in the urban area viewer, which allows us to basically establish the different loads for different municipalities within a given watershed. And we found that for Patton Township, the new modeling estimated a new baseline load of 572.8 tons per year. Therefore, using the 22% reduction requirement mentioned above, the sediment reduction target for Patton Township can be calculated as 0.22 times 572.8 or 126 tons per year. We then use GWLFE to simulate BMP-based reductions that would potentially reduce the watershed load from the baseline load of 2,625.7 tons per year to a new load of 2,499.7 tons per year, which is the watershed baseline load minus the reduction target for Patton Township. In our case, we simulated a new reduced load of 2,476.8 tons per year, which represents a decrease of about 148.9 tons. This is about a 26% reduction from the current load. This is greater than a 22% reduction, and we could go back and reduce some of the BMP implementation in order to get it closer to 22%. In any event, we simulated a fairly simplified case. We looked at one municipality within one watershed, and things can get more complicated as you deal with multiple jurisdictions within one or two watersheds. However, what's been outlined is fairly typical of the type of analysis that would be done for an MS4 watershed improvement plan, or the modeling that would be done in support of such a plan. And that concludes our case study exercises that we completed as part of Unit 8. Good luck with using MapShed. If you have any questions, please address them to me at our website, www.mapshed.psu.edu. And please check this website for future upgrades and additional software tools that might occur in the future. Thank you.